Hello, everyone. Welcome to our presentation. We are from WSP, and today we're going to be talking about your roofs could be assets and not liabilities. So I, Danielle Vella, will be one of your speakers. And
I'm Jean Guillebac.
So just going to go through a little bit of what we're going to be talking about today. So we're going to set the stage with a bit of the impact of climate change on roofing. Then we're going to talk about the overview of low slope roofing and different types, go into some roof assessments, decision-making process, case studies, and then wrap it up with the future impact of today's decisions. So I already introduced myself, but just a little bit more detail. So I'm Danielle Vella. I started out with WSP in 2015 as a field technician in the built environment group, and I've been with the company ever since. Our group generally takes care of designated substances and hazardous materials assessments, oversight of abatement, industrial hygiene assessments, and our new department, the Environmental Health and Safety Department.
My name's Jean Guillebac. I work in the building science division at WSP. In my 40 years career in construction, I've worked in the federal government, school board, in the manufacturing sector, and in the contracting fields. Then as a specialist roof consultant for the past 28 years. I'm the leader of the Centers of Excellence at WSP, and I oversee the roof consulting services for the company. Danielle?
Great. So now we're just going to get into everything. So just to set a little bit of the background, we'll talk about the impact of climate change on roofing. So here you can see just an example taken from Toronto's Future Weather Study, issued recently, showing the impact of climate change over the next 25 years. So in the first column here, you can see there's going to be an increase in daily temperature maximum of about upward of 7 degrees Celsius. In the second column here, you'll see a 3 times increase in hot days, which is about 46 days. The next column here, you'll see 4 times the extended heat waves. And then we have nearly 3 times more rainfall intensities. So as you can imagine, this is going to cause a bigger strain on the cooling of buildings, of course, the wear on roofs, and then, of course, a strain on drainage capacities of roofs. So here's just another example showing the Toronto heating degree days, which has a bit of the historical data and the future data as well, showing where climate has changed and where it's going to go. So since 2000, Toronto has seen an average reduction of 10% in heating degree days, meaning we're getting warmer, and changing from a climate zone 6 to a climate zone 5. This is a real world impact, and predictions are that Toronto will be in a climate zone 4 within the next 20 years. So if we do enter a climate zone 4, there's going to be more pressure, as I said, on cooling buildings with a greater potential for energy consumption. So the importance of redesigning your roofs right now to help meet your future ready needs is very important. So this is a bit of more what's expected to come and what we're seeing right now. So more intense rainfall. So probably noticed there's been a little bit more rain, and there will be more rain. There's an overwhelming of the drainage systems of roofs and structural loading from this rain and heavier snow and the wet snow accumulations. And then in turn, there's expected to be some catastrophic failures in building structures. We also have more severe wind events, so currently and to come as well. So this is just an example, as you can see here, the fully adhered roofing system that has failed. And these pavers are actually acting as the temporary ballast solutions until there can be a fix. So to summarize a little bit about the climate aspects, we're expecting hotter, drier summers, some wetter and warmer winters, fewer heating degree days, rising ocean levels, and more extreme weather events. So as I sort of drove home in the the other points. We need to adapt, and a way of doing this is redesigning our roofs now while we can and being future ready to adapt to these anticipated changes. So now that I've set the stage a little bit about what we're going to be talking about today and the impact and the importance of becoming future ready, I'm going to give some background about the different types of roofs that we'll be referencing today. So for the purposes of this presentation, we're going to be talking about low slope roof types. So versus the steep slope roofs, which is a completely different topic itself. But there's two primary types of low slope roof, which is also referred to as flat roofs. So there is the protected membrane roof assembly, PMR, which is also referred to as inverted roofs or upside down roofs. And then we have the conventional roof assembly. So the main difference, as you can see here, is the types of membrane location. So with the PMR roofs, you'll see that the membrane is at the bottom or in between layers, with the insulation being protected at the top. And then with the conventional roof, you have the membrane at the top with the insulation layers protected. So next up, we have one of the types of conventional roofing, which is the built-up roofing, also known as BUR. So this has been around since the 1800s, making it one of the earliest type of membrane used for roofing. So one of the main characteristics is that it has 3 to 5 plies of asphalt or bitumen, as you can see here, reinforced with felts. And you can imagine that would make it a heavy roof. And it typically requires more labor as it's applied directly in the field. So you can see in this picture here that it's how it's applied in the field. Next up, we have modified bitumen roof systems. So these are really like an evolution of the BUR roofs, the built-up roofs that we just talked about. So they were developed and used around the 1960s. The main difference of these is that they're usually 1 or 2 plies of membrane layers of bitumen. And so there's less redundancy in the layers in comparison to the built-up roofs. So some of the key characteristics with this one is that they're applied in place by either being mopped or torch application, which are adhered or self-adhered. So here you can see some examples of that and the torch here. Next up, we have the single ply roof systems. So this was also developed around the 1960s with the key goal to be introduced to save costs in roofing and the overall construction costs. So the main features of these is that they're typically 1 ply of membrane, which as you can imagine would require less material, less cost, and generally less heavy, depending on what you would put on top of it, of course, and generally faster to install. So you can see in these pictures here that there's 2 different types of single ply roofing. So we have the thermoset and we have the thermoplastics. So the thermoset, it's either adhered or taped. So you can see in this picture here that they are taping at a joint. And then the thermoplastics, the seams have to be welded. So you can see in the picture here, they're using a hot air gun to weld the membrane to the seams. So here's just some examples of how these single ply roof systems are generally installed. So there's a mechanically fastened system. So you can see in this first picture here, they are partially attached at the seams and perimeters with different mechanical fasteners. And then in this middle picture here, that you can see that it's being fully adhered. And then in this last picture here, it's more of a loose laid, and then ballast is laying on top. And of course, for all systems, the seams are welded and then adhered to provide the water tightness that you're looking for in a roof. And then next up, we have some other types of low slope roof systems. So the first one that we have here is a liquid applied hot rubberized. So their elastomeric coatings are hot applied rubberized asphalt and then reinforced. The second one here is spray foam and coating. It's a little bit more rare in Canada. The foam acts more of as an insulation, and then the coating acts as the waterproofing and UV protection. Next up, we have the hybrid built-up roof and mod bitumen. So this is really just a built-up roof with a mod bit cap, and then there's liquid applied with single ply over top of it. And then metal roof is just as it would sound, a metal roof. They are considered a low slope roof depending on the actual slope to drain properly. Okay, so next up we have a bit on roof assessments. So now that we sort of went into the different types of roofs, we can talk about how to properly assess your roof. So we have two different types of roof assessments. So the first one being a visual assessment, and then the second one being a comprehensive assessment. So visual would be just exactly as it seems. It's a visual assessment to determine any visible effects and repair to prevent further roof system damage. And it's, of course, limited to what can actually be observed. And it's more of a preventative maintenance approach. And then we have a comprehensive assessment, which is it's a more in-depth assessment with instrumentation to determine the presence of moisture within the roof. And then it also can involve the testing of roof system components or things such as designated substances and hazardous materials. Yeah. So the next, I guess a description of what roof thermography is. So it's a non-invasive assessment. So basically the goal of this is to detect infrared radiation, heat from different roofing materials. So wet insulation would retain heat a lot longer than dry insulation would. So the pros of this would be that it's, again, non-destructive and that it's relatively quick. So you can tackle large areas scanned in one evening, which is a big plus. And there's always the option for drone technology. Some of the cons or considerations would need to be that you need to have an accessible and compatible roof membrane. So it doesn't always work on protected membranes or inverted roof styles. And it's very dependent on environmental conditions. So it has to be in warm months, dry roof surface, low wind. So the conditions need to be optimal to do this test. And of course, it's subjective to interpretation of the actual results. So you can see here in some pictures, this is what it would look like through the scanner. And then this would be the tool that we would be using on site to conduct the survey. Next up, we have the EVFM testing, which is the electric field vector mapping. So this is to identify breaches in the membrane. So again, here's just an example of somebody using it in the field, and then how it works and a little bit more of an explanation, but just to go through, I guess, the main characteristics of it. So the pros is that it's a low voltage and non-destructive test. You can test through overburden to locate the membrane breaches, and it can provide exact pinpointing of the membrane breaches. It can be performed on sloped structural decks, and membrane defects can be repaired and retested without delay to the construction schedule, which of course is always extremely important. When you're trying to get a job done, you want to make sure everything is on schedule. And membrane performance can be monitored during its lifespan through the overburden. Some of the cons is that wet surfaces need to be present in order to actually complete the test, and that you need to have a permanent metallic grid system or some conductive medium in the roof to actually conduct the test. So next up, we have the comprehensive test. So this is, in our world, a designated substances and hazardous materials assessment. So DSHMA, or if you have ever heard of one or had to do one, it's commonly referred to as a DSS. So it's important to know when a DSS is required. So as a building owner or a project owner, it's important to know that your responsibility before beginning a project. So if you do choose to do the test and know what's on your roof and then replace your roof, it's important to know what's there, and you actually are required to. So as you can see here, Section 30 of the Occupational Health and Safety Act, before beginning a project, the owner shall determine whether there's any designated substances present on the site and then provide a list of the designated substances that are present on site. So what is a designated substances and hazardous materials assessment? So if you aren't sure what it is, I'm hoping it's because you haven't been doing any constructions or renovations, and it's just because you haven't heard of it before. But if you don't know, that's fine. That's what I'm here to explain. So basically, it's a detailed investigation or walkthrough of your building, conducted, of course, by a competent person or a consultant to identify materials suspected of containing designated substances or hazardous materials. So the survey aims to identify a few things. So the first thing would be the location of any suspected materials. That's designated substances or hazardous materials. The bulk collection of samples. So technically the bulk samples that are collected are really just mold, asbestos, lead, sometimes silica, PCBs. Those are just the common ones. Of course, you could test for anything, but those are just the common ones. The condition of these materials when they're observed. So if anything is in poor condition, it is also your duty to take care of it to prevent any further risk to the building occupants or workers. And in the case of asbestos, the friability and the type. So friability, if you're unsure of what that means, it's if you can pulverize something with the force of your hand. And then the type, so there's multiple different types of asbestos. I don't need to go into that, but different types, because that's important for the removal. And then, of course, for the building owner's use and purpose, some drawings, plans, or specifications. And really, depending on the scope of work, this survey can be intrusive or non-intrusive. But in the case of roofs, if you're going to be replacing your roofs, of course, the only way to tell is to do an intrusive survey. So that's where we would get into a pre-construction, renovation, or demolition assessment. So in the case where you would just be doing something as you're replacing your roof or testing something on your roof, this would be more of a project-specific assessment. So that assessment would be performed prior to the start of a project that could disturb the building materials that can contain a regulated substance. So as I said, this is your duty as an owner or building owner or project owner to be able to provide this information. But the good thing about these surveys is that it's only to assess the areas and materials specifically disturbed for part of the scope of work. It's also important to note that there's no exemption for recent construction or for the date of construction of the building. So we do get this a lot. My building was built in the 1990s. I don't need a survey. They weren't using asbestos or lead. You'd be extremely surprised. And there is no exemption. But it is good to note that it's not required for daily and non-construction projects, or as they're covered typically underneath other occupational health and safety legislation, such as WMIS or workplace exposure assessments. They're in place to protect the worker. And then, of course, regular maintenance projects that's not going to damage any hazardous building materials or designated substances. You do not need to do a survey for those cases. And as I said, roof is an intrusive investigation. So you can see in this picture, this is just an example of how we would test it. So this would be a roof core. And then we would typically sample for asbestos. The top layers here, maybe a middle layer of tar. And then usually there is an asphalt layer or tar paper at the bottom, and those can all potentially contain asbestos, which is important to know if you're doing renovations. So just a little bit more information on this. If I haven't explained it well enough, there is a guideline presented here by the Environmental Abatement Council of Ontario. So you can see here, this is just an example of what it looks like. Environmental Abatement Council of Ontario is now recently Canada, but they released a guideline to help understand pre-construction projects and your duty as a project owner. So the reason for this mainly is that there's significant variability in content, scope, methodology throughout different reports. So this is just a guide to help provide one sort of template or guideline. So three main goals of this is to create consistency within the industry, clarify the responsibilities of building owners, and then of course for the protection of workers. And this is an important document, although it's not a regulated legislation. It's created with input from consultants, contractors, labs, building owners, and ECO does actually provide input onto abatement legislation as well. So they're very involved. So just an example of the designated substances. So there's 11 in Ontario. We definitely don't need to go through all of them, but I've highlighted some of the ones that we're going to talk about today. So asbestos and lead being the main ones. Of course, you can find things such as benzene or silica on roofs, but for the purposes of today, we'll just go through these ones and then some of the additional hazardous materials that you could find on roofs. So ozone depleting substances and coal tar pitch will just be the ones that we'll go through today. So to start off with asbestos, there's an estimated 3,000 products that could potentially contain asbestos. Again, we don't need to go through all of these, but you can see I've highlighted the ones that you would normally find on a roof. So base flashing, caulkings or putties, you can find that on any doors, on flashing, vents, anything like that. Cement siding, cement wallboards, so this would be an asbestos cement. And then heating and electrical ducts, high temperature gaskets, HVAC duct insulation, roofing felt or roofing shingles. You would see here, there's typically roofing felt underneath these shingles. And then texture paints and coatings. So that's typically what's you would see on like soffits. Okay, so here's just a visual representation just to really drive it home for you. So we definitely don't need to go through what's in the entire building, but at the top, if we focus on the roof, you can find where you would find asbestos, typically in commercial and industrial buildings. So the flexible fabric joint here on the ductwork, in the actual roofing materials, which we talked about a little bit, roofing paint, so asbestos or lead, and then fire doors, of course, any pipes leading to the roof or on the roof as well has the potential for lead or asbestos as well. So just a little bit on the other designated substances and hazardous materials that you would see on a roof. So as I talked about, there's plenty of hazardous materials or designated substances, but just for this, we're going to focus on lead, which can usually be found in paint or solder or flashings, coal tar pitch, which is the tar material typically in the roofing membranes, and then there's the ozone depleting substances, which can be found in as HVAC or air conditioning refrigerants. So just to get into a little bit about lead on roofs. So this was used for centuries because its malleability, sealant capabilities, longevity, and corrosion resistance, which are all very important things on a roof. Typical uses for lead on roofs include flashing. So you could see in this example right here, this is a full lead flashing. The color kind of gives it away as well. The painted surfaces, so soffits, fire doors, flashing as well. So you could see something like this picture, it's brown paint. It's chipping off of the, I guess this would be just a smaller metal roof. And then here on the siding as well. And then in this case too, there was soffit paint that was chipping away. Of course, this can be found in mortar, and silica can also be found in mortar. And then pipes, of course, rainwater leaders. Typically, we would do bulk sampling for something such as paint bulk, so paint chips from different colored paints. Wouldn't really test this for lead unless we need to confirm it, but typically we can visually confirm stuff like that. Next up, we have the coal tar pitch on roofs. So this is widely popular for its resiliency, water resistance, and low melting point. And it's a byproduct of processing coal into coke. This, unfortunately, is a carcinogen as it contains harmful chemicals such as benzene, which is a designated substance, and polycyclic aromatic hydrocarbons, also known as PAHs, and has a very distinct odor. So if you've ever smelled coal tar pitch, you likely will remember that you smelled coal tar pitch. And then sampling and a laboratory analysis usually conducted to determine the presence. If the smell typically isn't enough, we could do sampling in laboratory. And one big thing for coal tar pitch is that PBE is essential for removal, as it causes chemical burns and extreme skin, eye, and respiratory irritation. So don't want to mess around with that. And the last thing I just want to touch on today would be the ozone depleting substances. So typically this is used as a refrigerant in air conditioners or HVAC units. And the most common one that we see is R22. It contains harmful hydrochlorofluorocarbons, so HCFCs, which contribute to ozone depleting ozone depletion. So you can see in this picture right here, this is where it would be seen on a label. So it says refrigerant and R22. So it is the intention of the government to phase out the use of ODSs by the year 2030 in order to protect the upper atmosphere. Of course, more of a focus on the environment now. And the equipment containing ODSs should always be recycled following the appropriate regulations. Here's just another example of a cleaner version of it. So this HVAC unit in this case says that it contains the refrigerant R410A, which is a more environmentally friendly refrigerant. All right, so I will pass it over to Jean-Guy to talk about the decision-making process for replacing or salvaging your roof.
Thanks, Danielle. So 50% of today's existing building stock will still be in use in 2050. Next slide, please. For existing buildings, decisions we made 20 years ago have had an ongoing impact on the performance of roofs over this time period. How we deal with existing roofs in place will continue impacting the performance of these buildings for the next 20 to 30 years. Do we replace all roof components, or do we consider salvaging some of these existing components, further prolonging their service life? For new buildings, keep in mind that the building codes today focus on new construction. Roofs being installed today will therefore be on most of these buildings 30 years from now, unless they fail in their performance before that time period. Design decisions made today will have to be addressed in the future, and planning for this future is crucial in today's environment. We've talked about climate change earlier, and can predict that building performance needs to be enhanced based on future trends. How do we make decisions? So some key decisions have to be made when it comes to roofing. Necessity, performance, environmental impact, and as a result of the decision, cost. We need to consider options, whether to recover or resurface, leading to waste diversion, deferral of work, or wholesale replacement implications. How do we define salvaging? Next slide. Salvaging is leaving a portion of the roofing components in lieu of removing and replacing the full roofing assembly, the insulation, vapor retarder, or thermal barrier, or setting aside some materials to reinstall in the case of the PMR roofs, the roof ballast. Some of the goals for salvaging, it's doing our part for the environment. Landfill diversion is one of the main problems for methane production. Others include cattle and agriculture. Reducing new product manufacturing. Addressing climate change needs. Another goal is to reduce costs for clients. A lot of times when we're talking about environmental approaches, there are additional cost implications, but in this case, in roofing, we can actually reduce costs, and I'll show that later on. We have less materials to remove, less landfill costs, reduce garbage hauling costs, and others. And also we improve project efficiencies. It's less disruptive to occupants, less noise, a faster schedule of work. Considerations for salvagings, we should consider the condition of the components in place, the type of components that are in place, the feasibility of salvaging such components, the cost and scheduling, warranty implications when it comes to salvaging and keeping materials in place, how the manufacturers see their warranty implications on that, and the impact to the building. Some noisy removals of some of the items, it can be very disruptive. Providing value-added service to clients, and basically, how old is too old on the materials to salvage. So when it comes to various renewals, I'll talk about in the next slides the different types of renewals that can be done based on the different roof systems that are in place. Danielle talked about the different types of roof systems, so I'll talk about some of the renewals here. And so when you're looking at renewing over old mechanically fastened single ply roofs, you could actually cut out the existing membrane near the fasteners, remove that membrane, leave the existing insulation in place, add additional insulation and new overlay board and new membrane on top. You can your option at that point is to install either another single ply membrane or additional or other types of membranes like built-up roofs or modified bitumen roofs. Keep in mind that the weight of the initial roof would have been a lot less. Therefore, you have to really keep in mind the structural implications of adding more weight to these roofs. When it comes to renewing of the BUR roofs, we've had our options we followed is to actually skin or remove the existing membrane and remove the gravel surfacing first, remove the membrane, look at how the assembly is fastened. So if you have good insulation underneath, you add mechanical fastening to the system. Make sure that you meet the wind uplift requirements at that stage. You can increase the R value of your roofs by adding additional insulation, an overlay board, and then another membrane on top. So you can go back with a built-up roof, or you could go back with less heavy membranes like modified bitumen roofs or single ply roofs at that in this instance here. When you're renewing PMR roofs, inverted roofs, where the membrane is located at the bottom or underside the insulation and overburden, you could actually leave the existing roof membrane in place remove temporarily the ballast that is there if you want to reuse it, and store it aside. And also some of the insulation that is in place. And that insulation must be, however, sound. Some of this type of insulation is an XPS insulation that has limited absorption of moisture. But I've seen a lot of this type of insulation also that has absorbed moisture and has to be disposed. So you have to be aware of that some of the insulation can be salvaged also, depending on how it was placed above the membrane. It could actually be bonded to the lower membrane, and once you remove that insulation, it is contaminated and would have to also be disposed of. So you could, I talked about leaving the existing membrane in place if it is sound also, and applying another membrane on top, either a modified bitumen membrane or built up roofs, or in some instances, single ply roofs. When another option, when you're looking at an older aged modified bitumen roof membrane, you could actually leave the whole assembly in place and apply one or two more plies of modified bitumen membrane on top. I will talk about this further in a case study too. So now we're into, I'll be talking about two case studies. Case study one takes place at Hamilton, a shopping center in Hamilton. Next slide, please. So in 2020, as part of a multi-year replacement program at this property, a project was carried out to replace several roof sections with a mix of types of roofing work, basically. We looked at salvaging materials on the two larger roof sections at the top, like you see here, and we replaced completely all the roof components at 5 smaller roof sections. So the total area of the salvaged roofs is about 62,000 square feet, which represents about 88% of the total project. And the total area of the smaller roofs, 12%, is about 8,600 square feet. So on the salvaging portion of the work, so we're leaving the existing roof system in place. We remove the built-up roof that is over a wood fiberboard overlay and isocyanate insulation, vapor retarder on a metal deck. So the only component that we're removing in the salvaged areas is the built-up roof. And then we mechanically fastened an asphaltic overlay board for wind uplift resistance. We adhered new insulation and overlay board, increasing the thermal performance from an R12 to over an R20. And we've applied we're applying a 2-ply modified bitumen membrane. So in order to actually carry out a successful salvaging project of this nature here, we need to do our due diligence. And as Danielle explained earlier, the roof thermography process was carried out to determine the location of moist areas. And in this project at the salvaged roof sections, we found about 890 square feet of moisture damage or wet areas. This represents only 1.4% of the total area of 62,000 square feet for the salvaged areas. So we confirm the moisture damaged areas to repair by doing cut tests and verifying that the moisture is present. And identified this on a roof plan location on the roof plan. And this, in the next slide here, I'll talk about the sequencing of the work. So on the first sequence was to remove the gravel surfacing. Most often now it's vacuumed off the roofs. Used to be you had to broom that in areas, cart it away in wheelbarrows, dump it off. Now there are large vacuum equipment that with hoses that you can go on the roof and vacuum all the loose gravel off. Then the contractor would cut the existing built-up roofs in squares and remove that roof from the covering right now from the overlay board, which is the fiberboard overlay that you see as a light membrane there. And then on the right side, you see that they're installing the new asphaltic overlay board. So you don't have any exposed deck in this sequencing, and you have minimal debris inside the occupied stores during this whole sequence of work. The next photo shows the overlay board mechanical fastening. To make sure that we meet the wind uplift requirements for the assembly. And then the application of the insulation. In this area, there's tapered insulation to allow for a better drainage for the roof assembly. That insulation was adhered in place, and an overlay board is adhered in place, and the base sheet modified bitumen membrane is applied. You can see that in the background. And then you finish off with the application of the membrane cap sheet. And in this instance, it was a torch application. So next, what are the landfill implications of this, of salvaging the roof sections here? Some interesting facts about this project to highlight include the impact of landfill. That the salvaged two larger roof sections, a total of about 62,000 square feet. The total weight of materials salvaged, so the insulation, vapor retardant, and the overlay board that were left in place, was about 72,000 pounds or 33 metric tons. That didn't go to the landfill. In when we look at the smaller roof sections, which represents only 12% of the project, the materials that were went to the landfill amounted to 51,000 pounds or 23 metric tons. That represents 41% of the total project landfill. What is the cost impact of on these salvaged roof sections? There are significant cost savings that were realized on the salvage roof sections. Approximate cost of the project was about less than $12 a square foot for the area of about 62,000 square feet. So a project value of about $735,000, as compared to a full replacement value of that project replacing the like-for-like components, the project would be well over $1 million. So total savings of $365,000 was achieved as a result. All these savings and other considerations such as trucking costs, manufacturing processes, energy efficiencies with increased R values, time and labor savings can all be calculated and used by the client for their environmental impact statements for their property. If you consider that nearly every year, part of the roofs at the property are being replaced, there are cumulative savings to be realized and significant environmental and energy benefits to achieve. So case study 2, membrane resurfacing project. with the goal of extending the roof life cycle. Next slide. For more than 20 years ago, a roof replacement program was undertaken at a property in New Brunswick. The total property roof area was over 750,000 square feet, composed of built-up roofs throughout. Over time, all built-up roofs have been replaced with modified bitumen roofs. Several of these sections applying the salvaging strategies as noted in case study 1. The impact of replacing these roofs with mod-bit roofs systems resulted in an average roof weight reduction of more than 5 pounds per square foot. This overall weight reduction allowed the option to consider resurfacing the existing roofs without removing any of the existing roof system components. So in 2019, a roof resurfacing program was undertaken based on decisions made in 2000 to replace the BUR roofs with mod-bit roofs. So this 4-year roof resurfacing program was tendered in 2019, and it looked at a phased work sequence starting at the most worn roof sections of modified bitumen. In 2019, the roofing costs were based on leaving the existing roof system components in place and adding a 2-ply mod-bit roof membrane. The total area for the 4-year program is about 175,000 square feet, which is about 23% of the total mall roof area. So as I showed in the previous slide, the concept is to leave the existing roof system in place and apply 2 plies of a new modified bitumen membrane. In this instance, no additional insulation can be installed to increase the thermal performance of the roof system in place. But this is a very simple solution, but that actually really requires several steps. Again, a due diligence has to be made in the design phase of this project to determine the areas of what insulation and repairs needed. There were minimal roof areas, I think less than 800 square feet of total roof area of 175,000 square feet was identified as wet. So we verified, with respect to the due diligence here, we had to verify the attachment of the existing roof systems in place and review of the existing surfaces. So we had to prepare specifications that clearly outline the roof surface preparation, so the cleaning of and removal of granules, the repair of blisters, ridges that were present in areas, looking at the perimeters and openings to prepare those areas properly with granule embedment in accordance with requirements for application of the new membranes, and also looking at drainage. So in areas that had some pooling water, we looked at adding some drains as needed, adding tapered insulation in some of the areas, and also adding overflow scuppers for future problems with future rainstorms in the areas here as an emergency overflow. Our details are important to develop. In this instance, we developed details alongside the manufacturer because some of these considerations were not done beforehand. So detailing at the perimeters and openings, detailing at the membrane torch application processes. We used a hybrid application process where the membrane was torched in place in the field, and picture framed around the openings and curbs and areas that needed to be adhered in place. At the time of the construction, we provided also field quality assurance work with the roofing contractor to verify compliance with the design and the manufacturer's requirements, including verifying the existing surface cleanup and preparation process, the primer application process, and addressing some site conditions such as area delaminations. The photo on the left shows the next slide. The photo on the left shows the old membrane cap sheet that has been cleaned and prepared for the new membrane, and the new base sheet membrane applied. On the right photo, we see the new base sheet and the new membrane cap sheet completed at the drain location. So some real interesting observations here. The estimated roofing cost, should we have replaced all components, was around over $13 per square foot on average. So this would have, or nearly $14 a square foot. This would have brought a total replacement project value of over $2 million. Next slide. But on the resurfacing, the costs were greatly reduced down to less than $8 a square foot. So you can see the cost implications or the cost savings of more than $1 million over the 4-year period. Based on the savings realized, the client could actually resurface an additional 130,000 square feet of roof area. So it pays for nearly 3 more years of resurfacing in the future. Note that the total 175,000 square feet of resurfacing in 4 years is 23% of the total area of the building. So in today's dollars, this property will save more than $3.5 million over roofing related costs over the next 10 years. The foresight to install a roof system has allowed this significant savings today. With respect to environmental impact of this resurfacing project, we've realized the following in year 1 alone. Reduction of equivalent of 18 trucks of landfill, nearly 18% reduction, 40% reduction in CO2s, or 250 metric tons of waste, 16,000 kilometers less traveled on waste haulage alone. When we extrapolate this for the 4-year program, there would be 20 trucks only for waste haulage versus 92 trucks if we'd had done a full replacement. Over 900 metric tons of equivalent CO2 reduction as a result, more than 60,000 kilometers less travel on waste haulage alone. Next slide. When it comes to delivering new materials to the site, similar cost savings are realized. For year 1 alone, 4,500 kilometers. If we multiply that by the cost per kilometer, is $2,200. An additional 23 trucks would have been required for manufacturing this product, the new products, and delivering them. Over 20,000 kilometers has been saved by not doing this. This represents 82% less truck haulage needed to deliver new materials to the site in the first year alone. When we extrapolate that for the 4 years, it's significant savings of more than 82,000 kilometers saved in truck haulage alone. Next slide. So some of the benefits here is time savings and reduced disruption for users. Resurfacing for year 1 was 26 weeks alone, compared to full replacement at 40 weeks. So there's a 35% savings in time saved. For contractors that know this, they can win work and get onto other projects sooner. There's a reduced environmental impact and major cost savings on the project, as you can see. As for case study 1, all these savings and other considerations such as trucking costs, manufacturing, time and labor savings can all be calculated and used by the client for their environmental impact goals. This approach, in addition to saving costs, was to extend the service life of roofs in place for another 20 years or more. And based on performance conditions, another resurfacing program can then take place for an additional 20 years or more before the initial roof weight reductions realized when the original BOR roofs were replaced are even met. What is the future impact of today's decisions? Next slide. You know, there's a saying, the most sustainable buildings are the ones that are already there. We often speak about LEED buildings, net zero buildings, passive house buildings, but we don't always consider the enormous toll that demolition and new construction have on the environment. Reuse, salvage, recover roofs is imperative for sustainable future-ready design. What is enhancing the influencing the market? Climate change is influencing it in the biggest degree here. An impact on roofing insulation requirements. Next slide. Some of the uses, or when we're talking of how roofs will perform here, they need to perform now much more so because they're being used as platforms. Most of you know of green vegetated roofs, the photo on the left, but there are now concepts as blue roofs being installed, where storm water is detained and then slowly released over time through the use of flow control devices or structures, or by evaporation. Next slide. Several clients are contemplating the installation of rooftop solar arrays, or have done that already. They need to be properly designed, and roofs supporting these structures need to be the right ones to perform for the life of these systems or beyond. The photo on the left shows a ballasted system resting on the roof surface. The photo on the right shows structurally mounted, elevated installations separate from the roof systems, providing easier access. The photo also shows vegetated roofs incorporated with that. There's a new standard that was developed by the National Research Council and others, the CSA 123.26 addressing future climate change predictions and how to design roofs to be more resilient as a result for roof drainage and wind specifically. This is the first standard that is forward-looking, whereas other standards have relied on past climate data. It's important to consider this future thinking document in your next design decisions. So keep in mind that 50% of today's existing building stock will still be in use in 2050. And I think you really have to keep that in mind, that what you design today will have an impact in the future. Thank you, everyone, for attending this talk today. Danielle and I would be pleased to answer your questions.